Hello, welcome to the online science activity Design and Math Tessellations at Virginia Tech. In this video, we will cover the geometric principles underlying tessellation in 3 dimensions and highlight their relevance to living systems, materials, and architecture. Decorating a flat surface with a repeating polygon, such as a square, triangular, or hexagonal tile, while avoiding imperfections is known as tessellation. Regular polygons can create a vibrant, alternating color pattern of a parquet floor in a lobby, or can be seen in a honeycomb of a beehive based on a periodic arrangement of hexagons. Furthermore, irregular polygons can be used for enhanced artistic beauty, as in the mesmerizing graphic artworks of the famous Dutch artist Maurits Cornelis Escher, or in the girih patterns in the Selçuk Mama Hatun Mausoleum in Tercan, Turkey. Tessellation patterns can be visually appealing, address structural constraints, or both. Planar tessellation with just one shape, for example hexagons, is straightforward, but how can we tile a three-dimensional structure? The simplest way is starting with regular polygons, an equilateral triangle, a square, a pentagon, a hexagon, and so on. The second rule is that at least 3 faces must meet at a vertex. So let's join 3 triangles at a vertex. Let us define the terminology here. We will call each polygon a face, each of the boundaries edge, and each of the corners vertex. Folding the faces around the vertex forms a portion of a tetrahedron, meaning 4 faces. Here, the configuration is folded around the vertex labeled by red. Repeating the same operation around each vertex here will require 4 triangular faces and give rise to a closed tetrahedral structure. Here and henceforth, a star next to a label denotes that a corresponding foldable model can be downloaded on the Virginia Tech Science Camp website under Design and Math Tessellations activity. You can find the link to the activity below at the video description. For the assembly tutorial, click on the links appearing on the screen. Next, let's do the same for 3 squares meeting at a vertex. Folding them at a right angle will yield the configuration around the red vertex. Repeating that around each vertex will form a cube. And similarly, folding 3 pentagons joined at a vertex will cover part of a dodecahedron, meaning 12 faces. Repeating that around each vertex will form a full dodecahedron. Let's step back and interpret the second rule. If we had only 2 faces around each vertex, the structures would not be closed. But the rule states at least 3 faces, so how about 4 equilateral triangles around the vertex? We can fold these 4 triangles into the half of an octahedron, which means 8 faces, and repeating the same procedure for each vertex will form a full octahedron. And we can also place 5 triangles around the vertex, and folding a pattern with 5 triangles around each vertex will give rise to an icosahedron, meaning 20 faces. Next, can we have 6 triangles around the vertex? Now we are running into a problem here. Around the central vertex, there is no opening between neighboring edges to fold the 2-dimensional pattern into a 3-dimensional structure. In other words, when the total inner angle around the vertex occupied by the turquoise area is 360 degrees, the pattern cannot be folded. And the same applies to 4 squares and 3 hexagons as well. And this brings us to the third rule. The total angle around the vertex must be less than 360 degrees. In fact, if we look at the total angle swept by the area of the polygons in earlier examples, they are all less than 360 degrees. In summary, the polygons that fold into a platonic solid are an equilateral triangle, a square, and a pentagon, and they form platonic solids if and only if they obey the second and third rules. As a result, there are only 5 platonic solids: a tetrahedron, a cube, an octahedron, a dodecahedron, and an icosahedron. The Platonic solids were first studied by the ancient Greek scholars Pythagoras, Thales, and Euclid. They were prominent in Plato's philosophical writings, hence the name Platonic solids. We can find examples of the Platonic solids in our daily lives. A soccer ball with pentagonal faces follows the arrangement of a dodecahedron. Another nice example of the Platonic solids in nature are the capsids of some viruses, our minuscule yet highly infectious archenemies from the microbial world. A virus codes its functions and replication procedure into its genome. The genome is enclosed in a capsid, which in some viruses is surrounded by an envelope membrane. Proteins such as enzymes inside the capsid, or envelope proteins that guide the invasion into a host cell, are integral parts of viruses. In general, the capsids come in two geometries: a helical arrangement of protein subunits that contains the genome, or an icosahedral arrangement that has 60 protein subunits or its integer multitudes, such as 120, 180, or 240 proteins, and so on. Some viruses, such as COVID-19, Ebola, or influenza, pack their genome into a helical capsid. Others develop icosahedral capsids. For example, a type of bacteriophage forms an icosahedron from 60 proteins, defined as T is equal to 1, where the T number is briefly a measure of the total number of proteins constituting the capsid. Different colors, white and magenta, correspond to two different protein types. The human endogenous retrovirus consists of 180 proteins, where different colors again correspond to different protein types. Its T number is 3, namely it has 3 times 60 equal to 180 constituent proteins. Human hepatitis B virus has 240 proteins, corresponding to T is equal to 4, and marine virus SYN5 has 420 protein subunits with T is equal to 7. The viruses are shown to scale, and their foldable models can be downloaded at the link found in the video description below. These icosahedral virus capsids are an elegant manifestation of Platonic solids in nature. But as for polyhedra, are we confined to Platonic solids, or can we design more complex configurations? In fact, by cutting or expanding the Platonic solids in certain ways, we can build 13 new polyhedra, with each of their faces being regular polygons. These 13 polyhedra are named after Archimedes, who is claimed to have listed them first. Later, they were widely studied during Renaissance and also by Johannes Kepler. Note that when we start building each of the 13 Archimedean solids, they will appear one by one in the bottom 2 rows. Now let's define the first operation, a truncation of the surface at each vertex. If the edge length of an icosahedron is L, the truncated portions highlighted will correspond to a length L over 3. Removing the highlighted regions will lead to an Archimedean solid, a truncated icosahedron, which is a geometry widely associated with the canonical soccer ball. Next, let's apply truncation by an edge length L over 3 to each of the Platonic solids. Truncated tetrahedron, truncated cube, truncated octahedron, truncated dodecahedron, and truncated icosahedron, which we have already covered. Next, we will truncate the surface around each vertex at a different length ratio. If the edge length of an icosahedron is L, the truncated portions highlighted will correspond to the half of the edge length, namely L over 2. Removing the highlighted regions will lead to an Archimedean solid, an icosydodecahedron, and we will explain the origin of its name shortly. Again, let's apply truncation by an edge length L over 2 to each of the Platonic solids. Truncating a tetrahedron by L over 2 yields an octahedron, another Platonic solid. Truncating a cube or an octahedron produces a neo-Archimedean solid named cube-octahedron, simply because it can be obtained by truncating either a cube or an octahedron. Truncating a dodecahedron or an icosahedron gives rise to an icosydodecahedron, again because it follows from a truncation of either an icosahedron or dodecahedron. Because truncation of both the cube and octahedron forms a cube-octahedron, we will call the two structures the duals of each other, and therefore a dodecahedron and an icosahedron are also duals. The second operation we define is bevel. Bevel is an even truncation of the surface along the edges. Let's take a cube and highlight the portion of the surface to be beveled along one edge. Then we label several other regions to be beveled. If we perform this operation along all edges and remove the highlighted regions, the remaining structure is a small rhombic cuboctahedron, an Archimedean solid with 26 faces named by Johannes Kepler. The next operation is snub, which is essentially successively applying truncation and bevel to a Platonic solid. Snubbing a cube yields a snub cube, and a dodecahedron a snub dodecahedron, as seen on the first row below. The last operation required to obtain the remaining three Archimedean solids is expansion, seen in this animation, a radial translation of all faces of a dodecahedron in blue or an icosahedron in red, while preserving the shape and area of faces produces a small rhombic quasi-dodecahedron. This is because icosahedron and dodecahedron are dual Platonic solids as we have covered previously. The great rhombic cuboctahedron and great rhombic quasi-dodecahedron are formed by the expansion of their small counterparts. These are the 13 Archimedean solids. They are all obtained by truncating, beveling, or expanding Platonic solids in certain proportions. They all consist of a unique arrangement of regular polygons in three-dimensional space. We can of course build even more intricate shapes. For that, consider the duality concept we have loosely defined previously between pairs of Platonic solids. We will start by making the definition of duality more precise. Imagine we find the centers of these 7 faces on a truncated icosahedron, which is an Archimedean solid, and connect the centers to each other by the red lines. The resulting grid here encloses triangular faces. Then, we apply the same operation to all faces of the truncated icosahedron, that is, find their centers, connect the nearest centers with straight lines, and highlight each of the enclosed triangular faces. The resulting structure is a new solid structure composed of triangles, which are not necessarily regular. This solid is called an Archimedean dual, or more formally a Catalan solid. Catalan solids take their name from the Belgian mathematician Eugene Catalan, who proposed them in 1865. 13 Archimedean solids have 13 dual structures, so there are 13 Catalan solids. The dual structure of the truncated icosahedron is pentagous dodecahedron, which can also be obtained by attaching pentagonal pyramid to each face of a Platonic dodecahedron. And another example of the Archimedean dual is pentagonal hexacontahedron, which can be created by taking the dual of the snub dodecahedron. And the 13 Catalan solids are shown below. Three-dimensional solid geometries have also inspired architects to build elegant-looking structures. The Amazon spheres located in the Amazon campus in downtown Seattle are a nice example to the close connection between architecture and the complex geometries of three-dimensional solids. The sphere's steel frame is formed by pentagonal hexacontahedron. Let's explore the pattern of a pentagonal hexacontahedron on this illustration of the steel frame when it was still under construction. These red faces constitute 4 faces of a pentagonal region. Next, we can find 3 faces highlighted in blue that are part of a neighboring pentagonal section. Last, we note that these 5 green faces form a pentagon that conforms with the red and blue regions. The identical steel units, each having a stem and 4 branches, constitute the skeleton of each of the faces. Here we have discussed Platonic solids, Archimedean solids, and Catalan solids. There are many other types of solids, of course, such as Dürer solids, Johnson solids, etc. But although the tessellation problem in 3 dimensions may seem challenging at first, one can incrementally build more and more complex arrangements starting from simple, regular polygons. and the resulting geometries prove highly relevant to the designs of many biological and man-made structures.